So the idea of an annuity in perpetuity is that it's an annuity that pays P indefinitely. And that's not that extreme way of thinking. Let's say you offer a life insurance policy for particularly people with jobs that are very risky. And heaven forbid I say this, it's designed for people that might get injured or die on the job. So you have people that might die at age 30, at age 40. So the family might get, a monthly annuity for 30 years, which would be 30, 40, 50, however many years. And, because you don't really know exactly when the person's going to die, this might be a policy aimed at this population. It could be anywhere, who knows? Maybe as a ballpark, you want to model this by an annuity in perpetuity, saying instead of saying, well, we have to make 40 times 12, 50 times 12, 30 times 12. Let's just say we just keep making these payments, and this is a conservative amount of how much we need to save to make these payments indefinitely. I mean, in real life, as I said, it's not really indefinite. It might be, 30 times 12, 40 times 12, 50 times 12, whatever. But just to keep the model simple, let's approximate for each person, as an approximation and as an approximate model. Let's say we're just going to make payments to the family indefinitely. All right. So, yeah, an annuity in perpetuity is just an annuity where payments are made indefinitely. And the time diagram is exactly what we had before. If we're doing an annuity immediate in perpetuity, the payment of P is discounted by 1 period. The next payment of P is discounted by 2 periods. Again, nu is present value factor 1 over 1 plus j. And we just literally keep going. Right, so we have this infinite series here. And if we factor out a P nu, then we know how to sum up this infinite series. Well, it's just our formula 1 over 1 minus nu is 1 plus nu squared, et cetera, et cetera. So here I'm assuming j is positive. This is a very long-term model. So it's safe to say in the long term, we have roughly, a constant interest rate. Or at least we have an interest rate that's positive in the long term. Things definitely grow in the long term. And, we're being simplistic here and assuming it's a constant interest rate for this whole period. Right. So remember here, it's nu is 1 plus 1 over j. And you do a little bit of algebra. This is just P over j. Really just, in the denominator, 1 minus 1 over 1 plus j. You get a common denominator. So it's 1 plus j minus 1 over 1 plus j. Anyway, do a little bit of algebra. This simplifies to P over j. So it's a very nice, simple formula. Right. And we're going to use this standard actuarial symbol A infinity j without the double dots for present value of an annuity immediate in perpetuity. So there's nothing funky going on here. This is a concrete, real number because let's think about what's going on. Yes, this is an infinite sum, but each of these terms here is worth less and less and less. Okay? So it's like saying we are going to give this family, let's say it's, I don't know, $1,000 a month. In 40 years, that $1,000 is, not worth that much compared to now. 80 years from now, the 1,000 is going to be worth even less. So in this model of in perpetuity, this $1,000, you discount it each period by the present value factor. It just becomes more and more and more worthless to the point where, you know, you're not adding up, you know, things to get to infinity. You're actually getting something that converges. The infinite sum converges. It's an infinite geometric sum. So this is like the, if I remember correctly, the macroeconomic multiplier effect, where in theory it's you get an infinite geometric series, but it converges because each, you know, effect has less and less and less value. Anyway, so right. So if we call A infinity j 1 over j, and this is, you can interpret this as p equals 1, so it's the present value of a perpetual annuity immediate with payments of p per period. Then the formula is just p A infinity j for an annuity immediate present value in perpetuity. You have basically the same timeline for an annuity due, just everything is discounted by one period. And here, deriving this is even simpler. It's just p times 1 nu squared. So it's p 1 over 1 minus nu. And again, a little bit of algebra. And it's just p1 plus j over j. And again, these two formulas are the same except for this except for this 1 plus j here. So it's, you know, instead of p over j, it's p over j times 1 plus j, which should make sense because, again, this timeline is exactly the same timeline as this, except we're discounting everything here by one period. One additional period versus this timeline. Okay, right, so just like before, we use double dots to indicate annuity due, and you know, when p equals 1, we use the this actuarial symbol A infinity j. So p double dot A infinity j is present value of annuity annuity due in perpetuity. Hello everyone. What I want to do is go over an example of using our annuity due and annuity immediate in perpetuity formulas. And this is an example that does appear in the exam FM every now and then. So we have an annuity due in perpetuity, offers $30 at the beginning of odd years and offers $40 at the beginning of even years. If interest is 3% effective annual, then find the present value of this annuity. So I would definitely draw a time diagram. Makes this problem really that much easier. So let's get to it. Okay. So, right. So here's my time diagram. So 0, 1, 2, 3, 4. And I don't really need to write any more than 4 years. Okay, so yeah, so here's year 1. Here's year 2, etc., etc. Year 3, year 4. So we were given that. Now let's just go back to the problem very quickly. We were given that at the beginning of odd years, so at the beginning of year 1, year 3, etc., the perpetuity offers $30, and at the beginning of even years, it offers $40. Okay. So, right, so at the beginning of year 1, at the beginning of year 3, and at the beginning of year 5, beginning of year 1 is t equals 0, beginning of year 3 is t equals 2, beginning of year 5 is t equals 4. So at the beginning of all these years, the perpetuity gives us $40 or pays out $30. And at the beginning of year 2, year 4, etc., so at t equals 1, t equals 3, etc., the perpetuity pays out $40. So, yeah, so I guess technically, not that it matters, but there really is no end, so there's kind of no point in drawing that bar here. So, like with problems we've done with different payments, not just one constant payment, we have to break this up into 2 annuities. So let's do exactly that. So let's start off with the $40 annuity. So before I do that, let's get the 2-year interest rate, because that's going to be what's relevant when we break this up into 2 annuities. So we obviously have the 2-year growth factor. Sorry. Well, we just get that, of course, by taking the 1-year growth factor, 1.03, and compounding that twice. So we get 1.0609. And so that means my 2-year interest rate, J, is going to be 0.0609. All right, so let's draw a time diagram for the $40 payments. Okay, so 0, 1, 3, etc., etc. Sorry, 40, not 30. Okay, so if I mean, maybe just if there's any doubt whatsoever, let's write one more. Don't think you really need to, but so let's write 5. So when t equals 5, we have a 40 here. Okay, so, right, so periods here are every 2 years. We have our 2-year effective interest rate at 0.0609. So this is an annuity in perpetuity starting at the beginning, at the second year of the second year, or the end of the first year. Doesn't matter how you think, really. So we use our formula, 40A double dot, and we want the present value at t equals 1. That's really important. So A infinity 0.0609. Right. Well, whatever that is. Sorry about that. I just want to fix the 9 here. So we have to discount this by 1 year of interest, remembering that the 1-year interest rate is going to be 0.03. Let me try and squeeze this. So exactly what I have written here. Okay, I'm going to have to move the 40 over here, move the arrow. Sorry about that. Okay, so you take exactly this here and just discount it by 1 year. at 3% effective annual interest rate. And you're going to get, this is going to be equal to 676 and roughly 52 cents. I'm just adding up these two annuities, so I don't really need to round any more than two decimals. But so this is just 48 double dot A infinity 0.0609, exactly what I have here. So what I'm circling is exactly the same thing. These two are exactly the same thing, just times 1.03 and minus 1. So I have to move it back 1 year. So it's 676.52. Okay, so let's do the next annuity. And this is why doing a time diagram is, I think, very useful for this problem, because it's, for me, very hard to organize exactly what's going on for each of these two different annuities in my head. If you can do that, great. I don't think I can. So, yeah. Okay, so 0, 2, 4, and this is the 30 payment. Okay, and this one's a little more straightforward. This is going to be just our annuity due formula. Sorry, 30A double dot infinity 0.0609. We don't have to discount this whole thing by any amount. And this is going to be 522 and 61 cents. Okay, so my answer, just add up these two annuities, these two present values. Let's just go back a second. Well, if you go back, it's 676.52 plus what we have here, 522, plus sign here, 522.61, and that's going to be $11.99.13. So I do like these problems because it really tests that you understand what's going on and understand how to handle mechanics of annuities as it pertains to exam FM and theory of interest. So this, yeah, I mean, this could very well be on a quiz or exam. I'll give homework. I'll give a homework very similar to this. Okay. So what I want to do next is talk about how to use the calculator to do annuity calculation.